Dear colleagues, we present to your attention a report on this topic, STEGANALYSIS method for detecting LSB embedding in digital video, digital image sequence. One of the most rapidly and effectively developing areas in information security in recent decades is steganography, the art of covert communication. The critical question is in whose interest the communication is being carried out. If its goal is illegal actions, the result of which may cause negative consequences for individual people, enterprises, banks, etc., and the state as a whole, then it becomes critically important to ensure the possibility of identifying such a communication channel, obtaining hidden information, which is within the competence of STEGANALYSIS. The preference for organizing a covered communication channel is increasingly given to digital video nowadays. Note that video can be considered a sequence of digital image frames. Therefore, in this work, such information contents are not distinguished. A video or an arbitrary sequence of images saved in the same format is considered a container. One of the most common steganographic methods today is the LSB method. The simplicity of its implementation, the possibility of providing a high capacity of a code communication channel, and the possibility of embedding decoding additional information in real time guarantee the method does not lose popularity in the coming years. At the same time, the task of effectively detecting the additional information embedded with this method will still be relevant. The problems of detecting the results of video steganographic transformation using the LSB method have already been raised by experts in many works. However, one of the STEGANALYSIS methods always allows us to speak about the final solution to the problem of video steganalisis, in particular under conditions of low capacity of covered channel. Recently, the authors of this work have developed a new approach to the problem of detecting integrity violations of a digital image based on the analysis of the dependency function of the frequency of the image matrix singular vector on its number, SNV approach. The basis of this SNV approach is the property of the SNV frequency linearity for the original image determined by the authors. This property is sensitive to distinguishing influences, which makes it possible to disturbing influences, which makes it possible to separate the original content from the one whose integrity is violated, particularly under conditions of minor disturbing influences. Taking into account the possibility of considering video as a set of images and the process of steganographic transformation as a particular case of disturbance, it becomes possible to use the SNV approach to develop STEGANALYSIS method for video. The SNV approach, taking into account the mentioned sensitivity of the linearity of the SNV frequency, should ensure the efficiency of the corresponding methods under conditions of low capacity of the communication channel. This slide shows the main aim and tasks which are sought in this work. Let F be n by n matrix of the digital image video frame. Equation 1 defines normal singular value decomposition F. The SNV, UI or VI, the elements of which within the SNV approach are considered as the values of some discrete function on the interval from from 1 to n, is associated with a quantitative characteristic which is the frequency eta, defined as 2. Let us define Fr as a function that reflects the dependency of the frequency of SNV, UI, VI, on its number I. As a result of the study of the FR properties, it was found that for original images in lossless format, the rate of increase for the trend of this function is practically constant over almost all the entire from 1 to n interval, which results in a property called by authors the linearity of the SNV frequency, both left and right. For the image video frame, the integrity of which is not violated, which means that the function fr is well approximated almost on all interval 1n by a linear monotonically increasing function L for the original image without losses. Here you can see it in slide as figure 1 AB. The linearity of the SNV frequency is a characteristic that is sensitive to any disturbing influences, including steganographic transformation. Figure 1C illustrates this. Violating the linearity of the SNV frequency for a non-original image video frame with embedded additional information will make it possible to separate it from an image video frame whose integrity has not been violated, parts of an empty container. Following the SNV approach, such as fundamental possibility can be effectively implemented even in the case of a low capacity of a covered channel. However, to develop an appropriate STEGANALYSIS method, it is necessary to obtain a quantitative estimate of the linearity violation of the SNV frequency, which is one of the problems this work solves. As possible quantitative indicators of the violation of the linearity of the SNV frequency for a video frame image, we consider equations 3 and 4, these indicators. Theoretically, a natural indicator of content integrity violation will be an increase in both 3 and 4 compared to the original image frame or the original video stored in a lossless format with any changes, including a steganographic transformation. It should be noted that the indicators 3 and 4, which were introduced naturally, unfortunately, as the computational experiment shows, do not fully provide the ability to separate the original content, a separate image video frame, from the one whose integrity is violated, taking into account only their values. The work justifies the choice of only one of two indicators considered quantitative parameters of violation of the SNV frequency. Thus, the parameter 4 is chosen and discussed further. For the work, taking into account that not every frame of the video, not every image in the sequence can be used to embed additional information during the steganographic transformation of a video sequence of images, it is essential to know how often in a sequences of images, video frames, the same or close L values are accepted and which of the possible values is accepted more often than others. The histograms of L values obtained for individual video frames or individual images of a sequence can be used to get such information. The histograms of L values for the container, the original in lossless format, sequence of video frames or images, and for the steganographic message, a non-original sequence, which is the result of the embedding of additional information into a container, will qualitatively differ from each other. From histogram gamma S will be shifted, the histogram gamma S will be shifted to the right along the OL axis relative to the histogram gamma O for the original sequence for any capacity of covered communication channel. Modes of histograms gamma S and gamma O respectively will be related by the following equation, this equation 5. With an increase in the capacity, the difference 5 between modes will increase due to the increase in mode of gamma S. All theoretical expectations have been confirmed in practice. This slide and the following slide shows the results. Based on the results obtained, the STEGANALYSIS method's main steps for examining a video containing n frames or a sequence of n images formally saved in a lossless format are as follows. This slide illustrates these steps. The results of evaluating the efficiency of the method using the indicator 6, including comparison with the analog, are given in this slide. As follows from the results, that the developed method provides high efficiency in embedding additional information into each video frame, increasing this efficiency by 1.5% under the conditions of capacity 0.1 bits per pixel. At the same time, type 1 error were not detected when testing the developed method done, which is its significant advantage compared to analog. The sensitivity of the property of the linearity of the SNV frequency allowed to get a more significant opportunity for the developed STEGANALYSIS method to gain efficiency in comparison with analogs with a small channel capacity. The maximum accuracy coefficient indicator is increased by 11.69% under conditions of a frame embedding rate of 40%. The main results and conclusions related to this work are shown in this slide. Thank you for your attention.